Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, welcome to another session of EPO 640 Electric Drive. So for this lecture, this will be part 3 of Electric Drive concept, method, design, and tools. Okay. So for this session, we will be discussing about the braking of electric motor. Okay, so using the examples of a DC motor drive. Okay, so a little bit explanation of the DC motor. Okay, so when a DC machine operates as a motor, the input to the machine is electric power and the output is mechanical power. And if the armature is connected to a DC supply, so the motor will develop a mechanical torque and power. Okay? And DC machine is used more than it's used more as a motor than a generator. And DC motor it can provide a wide range of accurate speed, and torque control. So that's why it's used as a motor more than a generator. So because you have more accurate speed and torque control. So for example, we will look into the separately excited motor. Okay. Separately excited motor, you have your so in this circuit diagram, you have your armature part. Okay, armature part of your. Okay, so this will sorry. Okay, so your separately excited motor. Okay, so this will be the armature part of your circuit, equivalent circuit. Okay, and this will be the field. Okay, field. So you have your in this case, this example, you have your field regulator. Okay, you have RF. Okay, and for your armature, you have RA. Okay, and IA, and you have your armature voltage. Okay, so VT will be the feeding voltage to the armature, and also VDC will be the feeding voltage to your field current. EA is also is the counter EMF and the value is in volt. Okay, so based on the equivalent circuit that is shown, okay, so you have EA equals to VT minus IARA. Okay, so that will be important equations. One of the 3 important equations that you need to memorize for this subject. Okay. So also shunt motor is quite similar to separately excited motor, but for shunt motor they shunt the what you call it is a shunt operation. Okay, so you have your input to your field and your armature is shunt. So it's the same. Okay, and it's represented by VT. Okay, so you have your input, input to your stator and your rotor. Okay, so it's the same. Okay, so you have your EA equals to VT minus IARA. Okay, and also VT is IF times RF. Okay, and you have your current. Okay, your current is I input equals to IF, plus IA. Okay, so this will be the equations to explain the circuit equations. Okay, and so for a steady state equivalent circuit, okay, so steady state equivalent circuit of the armature of a DC machine. Okay, just now we have EA equals VT minus IARA. Okay, and for the machine part of your, okay, for the armature, for the mechanical part of the equations. So just now we have discussed on the circuit equivalent circuit, equivalent circuit. So you have VT, okay, minus IARA, and this will be the mechanical part, mechanical equation. So you have your armature, okay. So the relationship between your armature and your speed, speed of your rotor, okay, is EA equals to, okay, KE flux times speed. Okay, so this will be a constant value. So in this case, okay, RA is the armature resistance, okay, and for the separately excited and the shunt motor is equal to the armature windings resistance. Okay. So the basic equations that is applicable to all DC motors are, okay, so the three important equations that you need to memorize. Okay, so you have your armature in volt, armature equals to KE flux omega m, okay, your speed, okay, relationship between your speed, okay, speed and your armature, okay, and this is according to your equivalent circuit. Okay, so for this is for shunt and for your separately excited. Okay, so if you have a series motor, so you'll be using a different equation here. And this is your torque relationship with your current. So this is torque, torque and current. Okay, so T equals to KE flux times the current, input current. Okay. Sorry, the armature current, not input current, armature current. Okay. So flux, flux per pole, okay, in Webers. Okay, you have your RA is the initial the armature resistance. Okay, omega speed of the armature. Okay, T is the motor torque, and K is the motor constant. And based on those three equations, okay, we can find the value of the speed. Okay, so again you have, okay, EA equals to KE flux omega m, okay, and also EA equals to VT minus IARA. Okay, so if we put it all together, so you have your okay, EA equals to K flux omega m equals to V, okay, minus IARA. Okay, not minus, yeah, okay, minus IARA. Okay, so then we can find the value of speed. Okay, so this will be put to here. Okay, and then you have is also equal to B over KE flux RA, KE flux IA. Okay, so IA and T is interchangeable. Okay, so you can based on the value that is available. Okay, so either T or IA. Okay, but T you have to your constant must be power to 2. Okay, what IA is you divided by KE flux. Okay, constant. So for motors type of shunt and separately excited motor, so you have a constant field current, okay, and the flux, the flux can be assumed to a constant value, okay. So in this case, you have your flux, your Ke flux, okay, and we can also consider it as a constant value K, okay. So that will make your assumption. So this is assumption. So you can further reduce, not reduce. You can enhance your equations. Okay, so for T equals to KIA. Okay, so a constant value. Ke flux as a constant value. Okay, or E equals to K omega m. Okay. So your speed, okay, will be V over K minus RA over KIA. Okay. So in braking, you have your motor. Okay, your motor works as a generator. Okay, so it develops a negative torque, which opposes the motion. Okay, so you have three types of braking. So you have your dynamic or rheostatic braking. You have your regenerative braking, and also you have your plugging or reversal of the voltage braking. So for regenerative braking, so in this mode, the energy is supplied to the source, okay, and this is the most common braking lah for electric drive, okay. So we harvest back the energy, okay. Okay, so let's say if you are driving a car, okay, when the car is moving, it uses energy, but when it brakes, when it go down the hill, okay, you can harness the energy of the gravitational movement, and supply back to your battery. Okay. So for this mode to happen, the following condition must be satisfied. Okay. So it must satisfy the value of your armature. Armature voltage must be higher than the voltage supplier. Okay. And it can also your current can also be negative, negative IA. Okay. Okay, but later on in our explanation on the 4-quadrant drive, okay, so sometimes it will not be a negative IA, okay, negative IA. So sometimes you have a positive IA that can act as a braking also, okay. But then the voltage, okay, the voltage of armature, okay, armature voltage, okay, must be higher than the supply voltage. Okay, so that this condition can happen. And sometimes you can regulate your field flux, okay, but then field flux you cannot increase beyond the rated value, okay, because of saturation. Okay. Hysteresis effect, okay, saturation or hysteresis effect. Okay. Okay, so if we look at regenerative braking, the example, okay, so let's say we look at this speed to torque characteristic, okay, under regenerative braking. So you have for condition 1, okay, so condition 1, which is when your vehicle is moving upwards, is in a forward motoring. So your motor has a positive speed. So in this case, positive speed is the speed turning at the clockwise. Clockwise. And you have your torque is also positive. Okay. So FM torque. Okay, your torque is T. T is in positive. Okay. So you can see that the car is moving, okay, forward, okay. So it's moving forward up until the tip of the heel, okay. So tip of the heel. So on the tip of the heel, instantaneously you have your car, okay, is recording a, okay, it's on a holding position lah, and we can say it's on the holding position. So you have your car at the tip of the mountain or at the tip of the hill, okay, okay, registering 0 speed, okay, dia berhenti 0 speed. But then you have torque, okay. So in order for the car to maintain at the tip of the hill, okay, so it has to have a torque lah, if it's okay, if it has no torque, so then it will go on reverse, or okay. Okay. So you have in this case during okay, during condition number 1, motor operation. So you have VT. VT is the voltage from the battery, okay. So supplying current to the armature and field, okay. So and it's on a motor operation, So condition 2, it's you have no speed stops, okay. And then when it goes downhill, okay, in condition number 3, okay. So you have your speed increases, okay, and okay, so you have in this case your EA is higher than your VT. Okay, so in this case, this is VT is higher than EA. Okay. So when EA is higher than VT, so you can see that voltage, okay, EA, the voltage in EA is higher than in VT, so you have your current flowing from armature to the battery. Okay. So this you can see that the direction of the current is in a negative direction. Okay, negative. Okay. So torque and current is interchangeable. So you can see that torque. Okay, torque is also negative. Current is also negative. Okay. So due to the direction of the direction of this current. Okay. So in this case, this is what we call generating. It's generating energy, okay, and supplying to the battery. Okay. So again, we can look it into the direction of the speed and also the torque. Okay. So in this case, you can see the torque load. Okay, torque load is in the anti-clockwise. Okay, so torque motor is clockwise. Okay. So TM and TL, okay, of course TM and TL is in a different direction. Okay, so TM positive. Okay, okay, so you have your okay speed. Speed is on the okay anti apa on clockwise. Okay, spinning clockwise. So you have it on a forward motoring. Okay, so when it go downhill, okay, so you have your TM is actually at the opposite side, okay, negative direction, okay, of your TL. TL is the friction or the inertia of the car, okay. But then your speed is still okay, spinning at the same direction, okay. And this can also be okay explained okay with this table. Okay, so you can see okay the direction of the armature current. Okay, So for motor operation, you have your armature current is in positive, your speed is positive, your field is positive. Okay. And if it's on the generator, okay, so your armature is in the negative. Okay, your load torque is also negative. Okay, and EA is higher than PT. Okay. Okay, and if we put it into the equations, okay, so this is so for equation, okay, so we would like to find what is the value of VT. Okay, so if we are provided with the value of RA, okay, IA, okay, so we can find the speed and also the current, okay, and also the torque, torque for this operation, okay. So this is for condition number 1, condition number 2, and condition number 3. Okay. Okay. So okay. So this will be a sample not sample a simple example. Okay. For you to try to do it. Okay. By yourself. Okay. So for tutorial, you have a separate set of questions in tutorial. So for lecture, if you want to understand so more about it, okay, so you can try doing this example, okay, by yourself, okay, and so I don't know if we provided, okay, no answers is provided, okay. But then we can discuss this the answers in our tutorial session. Okay, so tutorial session will be every Thursday from 3 to 4. Okay, so we will discuss the answers on tutorial session lah. Okay, so next we go to dynamic braking. So in this mode, the motor armature is disconnected from the source and connected across resistance. Okay, and the resistance is the RB, the connected resistance. So the generated energy is dissipated. Okay, so when we slot in the RA and RB, okay, so the generated energy is dissipated in both RA. Okay, so RA is the what you call it, the inner resistance. So most of the generated energy is dissipated in RB, the attached resistance. Okay, and since the series machine works as a self-exciting generator, okay, so the field connection is reversed so that the field assists the residual magnetism. Okay, so you can also flip the connection of the field in order to assist the braking. Okay, so this will be the diagram. Okay, okay, so you have your source. Okay, your source. So this will be the motor. So then if it's motoring mode, okay, so it will connect to A. Okay, so you have your motor connect to the source, so it will be a normal motoring mode. Okay, so when you want to brake it, okay, so they disconnect. Okay, you disconnect A, okay, and then you connect it to B. Okay, so it will connect to the resistors. Okay, and then you have your EA. At that time, EA will be higher than the load. Okay, the VB. Okay, so in this case, energy will transfer from the motor to the resistor. Okay. Okay, so and using different values of RB, okay, your connected resistor, okay, different value of RB. So you can see that the higher the value of resistor that you put in, okay, so you have the steeper, the speed will reduce lah. Okay. So as you can see, speed is the same, the direction. Okay, omega is in the same direction, anti-clockwise. Clockwise. Okay, and when it hits RB, when it connects to RB, so you have the system will based on the speed, so it will reduce. Okay, so let's say it's operating at A. Okay, so when it connects to RB3, so it will go starting from here and it will break down to 0. Okay, so when the current speed is at A, when it hits RB1, okay, it will automatically it will go to this region and it will break down here. Okay. Okay, so it can also be explained, okay, in this figure. Okay, so if you have your, okay, let's say you already know condition A, B, okay, and C. So C, if you have your, okay, when you hit the brakes, and when the speed is going backwards, okay, so and still you have your what you call it, your brake is still connected. So your brake is connected. Okay, so then there will be a okay, a negative generating. Okay, negative generating. You still have your current flowing from your armature to your to the resistor. Okay, but in negative. Okay, this case is because the speed. So when let's say if you are driving your car, okay, at a hill. Okay, so you hit on the brakes, you hit on the resistor RB1. Okay, so when it stops, okay, it will stop and then it will go downwards because of gravitational okay, gravitational torque. Okay, so then it will have a certain speed within the region. So for example, in C, okay, it will have a region, okay, where the speed will continue okay, to to turn the vehicle in a reverse direction. So C explains that condition. Okay, so both B and C is on a generating mode not generating mode it's on a dynamic mode. Okay, dynamic. Okay, because the power that is connected to the resistor is dissipated in terms of heat. So there is no power, okay, to be sent to the batteries. Okay. So how to calculate this some equations. Okay, equation on how to calculate. Okay, so okay, so this will be the I. Okay, I. So IB and I, okay, IRB. Okay, IRB, okay, equals to EA minus IA, okay, plus RB. Okay, so we have to consider for both RA and RB. Okay, and this will be the equations for power. So this will be the equation to find the value of either if they give the value of speed or they give the value of EA. Okay, so you can find the value of RB. And there will be an example here. Okay, so example on how to use this equation. Okay, so this also will be discussed in our tutorial session. Okay, hopefully. Okay, and also another exercise, okay, for you to do. Okay, so for you to do by yourself first. Okay, so same with this one. So this one is a very straightforward question. Okay, and this one you have to go through. You have to understand a little bit. Okay, the relationship between the using the three equations that you have learned just now. Okay, So they give you the torque, the torque value, and they want to limit the motor speed to 500 RPM. Okay. So what resistance must be connected across the motor terminal? Okay. So some of the hints. Okay. So to solve this equation, this problem. So first you based on E equals to IR. Okay. So find the value of R. Okay. And this will be a hint, the solution. So the blue is the value of the constant value, and the orange one is the value of torque. Okay. So of course you have to search for the value of K and for constant and torque. Okay. So based on the given, okay, based on the given value here. So this one is the value of EA. Okay, and you have the value of current. Okay. So using equations 1, 2, 3, okay, so you have to find the value of K and the value of torque. Okay, for each value of I and EA. Okay, simple. Okay, so last one will be on the counter or plugging. Okay, so in this mode, the supply voltage of a separately excited motor is reversed. Okay, so that it assists the back EMF in forcing armature current in reverse direction. Okay. So a resistance, okay, RB is also connected in series, okay, with armature to limit the current. Okay, so for safety purposes, and the series armature alone is reverse. Okay. So for counter plugging is you switch your they will switch the what you call it the terminal. Okay, so if you switch the terminal, so the positive will become negative. Okay, automatically. Positive will become positive will become negative lah. So you have the same power flow and so on. Okay, because it's negative. So yeah, if you look at okay, so TVR. Okay, so you have your during okay, in condition A, so you have your okay, source supplying to the armature. Okay, and if it's reverse, okay, so you have your speed also reverse, and also the source is also reverse. So it will go this way. Okay, so this one will go this way, this one for B it will go a different direction. Okay, but then what is different is the speed. Okay, the speed. Okay, so the direction, okay, so from counterclockwise, okay, when your motor is turning at counterclockwise, so you're forcing your motor to go clockwise. Okay, to go to go this way lah. To go this way. Okay, so this will create an braking effect lah. Okay, so okay, so this will explain the for V1 and V2. Okay, so the equations okay, for you to calculate, okay, for terminal voltage reversal. Okay, same thing, how to find the value of V1, okay, and I. Okay, so okay, so this one is 4, 3. So 3 will be the holding position. Okay, holding position. Okay, so same thing, explanation based on the column, based on the table. Okay, and we can do example. So this example will be discussed in our tutorial session. Okay, so if we have time. Yeah. So in the meantime, you can try to do it by yourself. Okay, and we will have some interesting discussion. Okay, during our tutorial session. Okay, so for that, thank you. And okay, so have a nice day.